In the last class, we were talking about the topology of defects. That is characterizing defects by this topological charge that indicates how many times the director rotates as you move about the central point. Today, I want to continue talking about defects, but a somewhat different point related to the energy of defects. So this is another example of using the Frank free energy to characterize how much energy is associated with a variation in the director field. Okay, so once again, I'm going to consider just the two-dimensional case, which is really much easier than three-dimensional. Okay, so let's think about a 2D pneumatic phase. And you know, we have the Frank free energy. All right, so the Frank free energy in the simplest form, that is, with the approximation of only one Frank elastic constant, that is to say, it's the same Frank elastic constant for any kind of director deformation. All right, so then the Frank free energy is this integral over the two dimensions now instead of three of 1/2 the Frank constant, and we could say del INJ, del INJ, like that. Okay, and now if we are working with a two-dimensional liquid crystal, we have that the director field as a function of position is some x component, the cosine of phi, and then the y component is the sine of phi. Okay. So we can take this expression for the director field and put it into this free energy to simplify and get the free energy expressed just in terms of the angle phi. Okay, so let's do that. Okay, so this thing, this means, well, the x derivative of nx squared plus the x derivative of ny squared plus the y derivative of nx squared plus the y derivative of ny squared. Okay, so thinking about just the first two terms there for the moment. Okay, so the x derivative of cosine phi squared plus the x derivative of sine phi squared. Okay, so that part is negative sine phi times the x derivative of phi all squared plus cosine phi times the x derivative of phi squared. All right, so that's sine squared phi times the x derivative squared plus cosine squared phi times the x derivative squared. So with the trig identity that we talked about last week, this turns into just the x derivative of phi squared. Okay. And likewise, this stuff over there is just the y derivative of phi squared. Okay. So the free energy with both of those pieces, we could say it's our integral over all position of a half Frank constant. Oh, and we could say, d phi dx squared plus d phi dy squared. Or even more compactly, we could write it as 1/2 k times the gradient of phi, this gradient vector squared. Okay, so this is the Frank free energy. Right? So we want to know, what is the Frank free energy associated with a defect? For example, with a defect of topological charge plus half, right? Which we know looks like this, right? That there's a director comes around like this. So here, there's a director which certainly depends on x and y, right? There's a function phi of x and y. So, over here, phi equals 0, and over here, maybe phi equals pi over 2. And here, phi equals pi over 4, something like that. Right? And so we want to know how big are the derivatives of phi, so then we can square them and put them into an equation like this and say, what's the free energy associated with the whole defect? Okay, so we need an equation for this thing. Right? What's an equation, right? Well, we want to minimize the Frank free energy in order to find this phi function. Now, the structure that I have drawn here is for sure not the global minimum of the Frank free energy. The global minimum is a uniform state like this, right? This sort of thing is the global minimum, where phi is a constant. But even so, there can be a local minimum of the Frank free energy, where phi is not a constant. Okay, and so what it means for a structure like this to be the local minimum is it's the best that you can do with just making small local changes in the phi function. And you would need to go to a completely different structure like this one in order to do even better than that. So if we want to make a local minimum of the Frank free energy, we need to use variational calculus, the same as we've been doing all semester. Okay, so a local minimum, like any other minimum, like a global minimum, that is a state where the variational derivative, the functional derivative of f with respect to phi of r is equal to 0. So we need to calculate what is the functional derivative of this function up here with respect to phi at some position. We've done problems like that a lot of times before, right? And we know that whenever we want to get the functional derivative of a first derivative squared kind of term like that, it turns into a second derivative through our integration by parts trick. Right? So in this case, the functional derivative of this f with respect to phi of r is going to be the k times the negative second derivative with respect to x. And so that's what you get from the first term. And then the second term, by the same kind of argument, gives us the negative second derivative of phi with respect to y, like that. So the combination of these things could be written as negative k times the Laplacian of phi. So that is what has to be equal to 0. Or if we cancel off the factor of negative k, we just get that the Laplacian of phi has to be equal to 0. This is the differential equation, now the partial differential equation, that we need to solve in order to get a formula for what is phi in this kind of configuration. It is possible to solve this in Cartesian coordinates or in polar coordinates, right? Either way works totally fine. Okay? So we could do it in Cartesian coordinates where we say, whoops, well, not very good pictures, is it? Let's try that again. Let's make the origin of coordinates right at the defect itself, okay? So we could say here's x, here's y. Or we could work in terms of polar coordinates, r and theta. Either way works, right? And so I will save time by skipping ahead to tell you the answer, okay? And so the answer is in polar coordinates, that is in terms of r and theta, then we get that phi could be any constant times theta plus another constant. So here, this Q is the topological charge. That's the same parameter that we were talking about last week. So what this tells us that, you could say, lets this make sense, to make this seem reasonable, is if you go about the full circle, that is, if theta goes from 0 up to 2 pi, then the angle phi goes from phi 0 up to q times 2 pi plus phi 0. So that means then that the integral around the circle d phi is equal to the ending value 2 pi q plus phi 0 minus phi 0. So that's 2 pi q. So that means then that the topological charge associated with the defect is q. So for the picture that I drew, the picture is a q equals 1/2. So in the picture, we have phi equals 1/2 theta plus phi 0. So what is the phi 0? Right? Well, the phi 0 tells us what is the value of phi at theta equals 0. So that means what is the value of phi along the x-axis? Okay, so here's the x-axis like that. And you can see in this picture that phi is about 0 on that axis. Okay, so in this particular picture, we have phi 0 equals 0. But if you change phi 0, that would give an overall rotation of this whole structure. Okay, so this is the answer in polar coordinates. By comparison, in Cartesian coordinates, that is xy coordinates, well, we know what the angle theta is if you convert between polar and Cartesian coordinates, right? That you get the angle theta from the inverse tangent of y over x. If that's maybe not familiar to you, what might be more familiar is to say x is r cosine theta and y is r sine theta. Okay, so if you take the ratio of those two things, that means that y over x is equal to the tan of theta. So theta is the inverse tan of y over x. Okay, so I'll just substitute that for theta in the equation up there. Okay, so we get then that phi is q times the inverse tangent of y over x, again, plus this phi 0 constant. So this is the equation that I used for drawing all the Mathematica pictures that I showed you on Friday. And I posted that Mathematica notebook in the Blackboard site. And if you download that, you can see about how to draw the pictures, right? And you can see a whole bunch of examples where I put in different values for Q and phi 0. And that's how I generated the pictures, right? And so I generated the pictures, right? So I got this phi, and then I said n is the cosine phi sine phi. Right, okay, good. So now we have this. So here now we have an equation for the phi angle in terms of either Cartesian coordinates or polar coordinates. Okay, you guys good with this so far? Any questions?
I guess you wrote something mistakenly.
Probably.
Below the topological chart there, there is phi, there's theta equal to 0, and you can get phi is equal to phi 0, right?
Uh-huh.
And when theta, sorry, I made a mistake. Sorry.
Okay, no problem. All right, so this then is our expression for phi as a function of position. Okay, so now we can put it into the Frank free energy, which we have right up there, in order to get the Frank free energy associated with having a defect. Okay, so the Frank free energy density then is this thing. So let's figure that out. So the Frank free energy density, that is per unit area in 2 dimensions, let's call that F density, that is 1/2 K times the gradient of phi squared. So I need to take the gradient of phi and square it, which I can do in either polar coordinates or Cartesian coordinates. Let's see, so I either have to differentiate this thing in polar coordinates or this thing in Cartesian coordinates. I would say polar coordinates looks easier. Okay, so let's do that. Okay, so in polar coordinates, we have an expression for what's the gradient of anything. This is like what you might have used in multivariable calculus or in perhaps electrostatics, right? You probably did gradients in polar coordinates. And so it is the derivative of phi with respect to r times r hat plus 1 over, whoops, not 1/2, 1 over r d phi d theta in the theta hat direction. So since our equation for phi is q theta plus phi 0, the derivative of phi with respect to r, that is 0. It doesn't depend on r. Plus 1 over r, derivative of phi with respect to theta is q in the theta hat direction. Okay? So this is just q over r in the theta hat direction. So this gradient squared, this thing dotted into itself, is q squared over r squared. So the Frank free energy density is 1/2 K times q squared over r squared. Okay, so far so good? Okay, so now let's plug that into the integral to get what's the total Frank free energy associated with the defect. Okay. So that is going to be the integral over all position of that Frank free energy density. So that's this k q squared over 2 r squared. Again, we can do this in polar coordinates or in Cartesian coordinates, whichever we find to be easier. Okay, so how about doing polar coordinates again? Okay? So you have to remember how to do integrals in polar coordinates. Okay? So in polar coordinates, you can do an integral over the whole plane. So the integral from 0 to infinity r dr, integral from 0 to 2 pi d theta, right, of the thing that you are integrating. Okay? So this is the measure of integration in polar coordinates. And you definitely need to include this factor of r in the front as part of the measure of integration. This is absolutely necessary to get the right answer when you're doing an integral in polar coordinates. So it's this integral of the thing that we are integrating, kq squared over 2r squared. All right, we need to do an r integral and a theta integral. Well, the theta integral is easy because nothing depends on theta. Okay? So that just gives us an overall factor of 2 pi. So we have 2 pi, and let's see, I'll factor out the k, I'll factor out the q squared, I'll factor out the half. We have an integral from 0 to infinity of r dr, and there's a 1 over r squared that needs to get integrated. Okay. So this is an integral of, well, pi k q squared, integral from 0 to infinity dr over r. And we know how to integrate 1 over r. That's the natural log. So this is pi k q squared log r evaluated from 0 to infinity. And now we look at this and we say, wait a minute, we have a problem here. In fact, we have 2 problems here. We have a problem at 0 and we have a problem at infinity. Right? Because if we plug in the upper limit of integration, that is this infinity, we get the log of infinity. That's infinity. Okay? Then if we plug in 0 at the lower limit, we get the log of 0, which is negative infinity. Okay, so this tells us that we have 2 problems that we have to figure out. So let's talk about how to deal with each of these problems. Okay, so these 2 problems are actually quite different from each other. And so I'll tell you about each of them in turn. Okay. First, let's think about the problem at r goes to 0. There is a word for this kind of a problem. Okay, so this is a problem at a short distance. And it is called an ultraviolet divergence. Why ultraviolet? Well, I guess that's just because ultraviolet light is a shorter wavelength than visible light. And so this is a short distance sort of issue. And so people say ultraviolet. Now, when there is a problem like this in not just in liquid crystals, but in any kind of condensed matter physics, okay, that means that we are applying the Frank theory at short distances, but it doesn't work at short distances. The Frank theory is a theory that works at long distances, assuming that the gradients of the director are not very big. Right? But if you have short distances, so that there's a big change in the director over a short distance, that means the gradient is really big there. And that's exactly the kind of situation where the Frank theory breaks down. Okay. So something goes wrong with the Frank theory when you apply it at short distances. Okay. Now, maybe you ask, what goes wrong? Well, multiple things could go wrong, but I'll tell you one thing in particular. You remember we have an expression for the Q tensor in terms of the director and the magnitude of pneumatic order. And you remember when we started thinking of this varying in position, we said, well, the S could vary with position like that, okay? But, you know, I'm going to assume that S is a constant. Well, not just me, Frank assumes that the magnitude is a constant. Okay? And so the only important variation is in the director, okay? That this varies as a function of position. Okay? And that's a reasonable assumption most of the time. Right? In most situations, the magnitude of pneumatic order is strongly constrained. Why is that? Well, you know, I showed you graphs when we were talking about Myers-Alpha theory, for example, that show you what's the free energy as a function of S. And, you know, maybe it has a peak, a minimum here and another minimum there. Okay, and so S is stuck here at this minimum. Right? That's a very good approximation almost everywhere. But the one place where it's not a good approximation is right in the middle of a defect. It breaks down right in the middle of a defect because the gradients of n are huge there. Okay? And so if we have a defect, here I'll draw one. Here's our half defect, something like that. The n is changing, say, by 45 degrees over a centimeter over here, but n changes by the same 45 degrees over a millimeter there. And if you get closer and closer to the center, n changes by 45 degrees over a micron or a nanometer or a very small distance, right? And so we could say that the gradients of n are big here at the defect core. And so the liquid crystal will respond to that in some way by changing S, okay? And so S might, for example, go to 0 at the defect core. So the Frank free energy breaks down, and it is no longer the case that the free energy density is just going to be equal to, it will not just be this 1/2 k times the gradient of phi squared. So what can we do? Right. Well, there are a couple options, right? One is we could try to make an improved theory, which includes variations in S as well as variations in the angle phi. Right? Alternatively, an easier thing to do is um, to say, let's just use the Frank theory for away from the defect core. So we'll use the Frank theory for R greater than R core, right? Some characteristic length scale where the Frank theory applies. So this would be something like a molecular length scale, something like 10 nanometers, say. And say, so we'll use the Frank theory for distances greater than 10 nanometers. But for distances less than 10 nanometers, we'll say, well, we don't really know what the free energy is, but it's something, we'll just call it a constant core energy for the defect. So in that case, if we go back to our integral for the defect energy, that is this integral, right? I will now write that this integrated energy, instead of being pi k q squared integral from 0 to infinity, dr over r, I'll just put in a core radius here. Say there's some core radius there. Or let me put it a better way. I could say we have the integral from r core to infinity, dr over r, plus something else that describes what happens for r equals 0 up to r core. And I'll just give it a name. I'll say, here is some energy, E core. That's the energy associated with the core of the defect. Okay, so we'll do that. Actually, in the text that I wrote, I used the letter A for R core, lowercase a. That's what people often do. Okay, so I'll use that now. So there's a defect core radius, which is this lowercase a. So this then is a way to solve the first problem, okay? To solve the problem that is associated with the behavior at short distances. Okay, so that's the first problem. Okay, this r goes to 0. Okay. What about the other problem? Okay, we still have a problem at r goes to infinity. This is a different kind of problem. It is a problem associated with long distances. For that reason, as you might guess, it is called an infrared divergence, because infrared light is a longer wavelength than visible light. And so that's the word that people use for this behavior where something goes wrong at long distances. Okay, so in liquid crystal science or anywhere in condensed matter physics, when you have an infrared divergence, it's not an issue of applying the theory where it doesn't work, because the theory really does work at long distances. It should work at long distances. Rather, it's a problem that the distortion is happening at very far from the defect core, right? That we don't just have a distortion concentrated at the defect core. It dies out gradually as you go to longer and longer distances, but it doesn't die out rapidly enough. It still persists enough to get an integral which diverges. So we can't really take the integral to infinity. But we have to say, well, that's okay because the experiment isn't infinitely big anyway. The experiment has some maximum size. All right, so we could just put in a maximum size, let's call it capital R max. And we'll say the experiment is not infinitely big. We just need to put in something associated with how big is the experiment. And so in that case, we get a free energy, which is this pi k q squared integral, now from A up to R max, dr over R, plus this core energy. So this then is an integral that we can do. We get pi k q squared times the natural log of R max over A plus E core. So this free energy depends on the whole size of the system, right? And so it might seem funny to think that the defect energy, that's the energy associated with this point, depends on the size of your experiment. But in fact, it's just a logarithmic divergence. And logarithmic divergences are very slow, right? And so if, you know, in the text, I did some examples, right? And I say, well, what if the A is 1 nanometer and the system size R max is 1 meter? Okay, that's a big experiment, okay? But still, the log of R max over A, that's the natural log of 10 to the 9. Well, that's just a factor of 21. That's not an enormous factor. It's a sort of modest factor. And even if R max is 1 kilometer, we just would have the log of 10 to the 12th, which is what, 28. So a log diverges, but it diverges really slowly, and we can live with that. It's okay. So here then is an expression for the energy of a defect. Right? And what can we see about it, right? Well, for one thing, there's this dependence on system size. For another thing, there's a dependence on the topological charge of the defect. It's proportional to Q squared. So that tells us that large defect charges have a lot more energy than small defect charges. So that's a reason why highly charged defects tend to break up. So for example, if you have one defect with Q equals 1, right, then the free energy is the pi k log R max over A. Or if we have two defects with Q equals a half, then we get a free energy which is 2 times pi k over 4, this log R max over A. Here I'll say plus E core plus 2 E core prime for a different kind of core. Okay, so in general, the second thing is smaller than the first, right? Because there's this extra factor of 2/4, 1/2 in front of it. Okay. So that's a reason why high Q defects break up into low Q defects. There'll be less defect energy associated with them. Okay, let me show you one more thing that you can get from the kind of calculation with the Frank free energy. What about if we want to study the interaction between two defects? So I showed you pictures in the class last week and also in the homework that you're doing now of systems that have two defects. Okay, so for example, we have a picture with 2 plus half defects, which might look like this. Right? You remember we looked at something like this in the last class. Right? So maybe we want to know what's the free energy of this system with 2 plus half defects. We can do that with the same kind of approach. That is, we want to know what is the function phi of x and y, which describes the system with two defects like this. This calculation actually is not as hard as you might think. When we are in the approximation of equal Frank constants, that is the simplest Frank free energy. Okay. The calculation is not so bad because the equation that we are solving is this variational derivative is equal to 0, which means that the Laplacian of phi is equal to 0. You'll notice that this is a linear equation. That is, everything here is proportional to phi. Because it is a linear partial differential equation, it has the superposition principle. That is, we can just add up solutions and get a new solution. So we can add up the solutions that are associated with a defect here and the solution that's associated with the defect there. So the solution, the sum of solutions would be something like phi of xy is the topological charge of the first defect times this inverse tangent of y minus y at the first defect over x minus x at the first defect, plus the same thing for the second defect, q2 y minus y2 over x minus x2. And again, plus a constant. Now, we can take this and put this expression into the Frank free energy. So we have F is the integral of this rad phi squared times k over 2, and integrate this overall position. When we do that, we will get some free energy that comes from the derivative of this term squared, and some free energy that comes from the derivative of that term squared. And then we also get a cross term, right? When we, here it's the square of the total gradient, so it includes a cross term. Right? So this whole thing gives us the free energy of defect number 1 plus the free energy of defect number 2 plus some extra free energy associated with the interaction, which might be either positive or negative. I will skip ahead and tell you the answer for what this interaction free energy is, and that's worked out more in the text. Right? But the interaction free energy is 2 pi times the Frank constant. We have a Q1 times Q2. That's reasonable because we're multiplying this term times that term. And then there is a log of R max divided by the distance between the defects. What shall I call that? How about R12? That is the distance between position 1 and position 2. So this then is an interaction which depends on the product of the topological charges, Q1 times Q2. In that sense, it might remind you of Coulomb's law. And so indeed, you could say, what's the interaction if Q1 times Q2 is positive versus what happens if Q1 times Q2 is negative? Okay, so this means if there are like charges versus opposite charges. If there are like charges, right, then this free energy has a positive coefficient in the front, and then there's the log of something divided by the defect separation. Okay, so that makes a negative log of the defect separation. So that means it is a free energy for the interaction as a function of the spacing, which is a negative log. It is a decreasing function like that. And so here, it's not such a good looking box, is it? Something like that. Okay, so this shows then that the defects repel. That is, they can reduce their free energy by moving apart to larger and larger distances. And by comparison, if we have opposite charges, then there's this negative number in front times the log of something over the distance, right? And this is a negative log. So the negative signs cancel, and we are left with an increasing function, something like this. So in this case, the defects attract. So, like charges repel, opposite charges attract, right? Have you ever seen something like that before? Sure, in Coulomb's law, right? In Coulomb's law for electrical charges. So this is another case where there is actually an interesting analogy between these topological charges and electrical charges. You might look at the dependence on distance, okay? So we see that the interaction free energy involves this log of the distance, okay? So if we take the derivative of that, that tells us that the force is the 2 pi k q1, q2 divided by r12. Okay, so the force drops off as 1 over distance. Okay, so maybe you're thinking to yourself, well, that's not like Coulomb's law, right? Because Coulomb's law drops off as 1 over distance squared. But you're thinking of Coulomb's law in 3 dimensions. Okay, what if we were in a 2-dimensional universe? Right? In a 2-dimensional universe, if you apply Gauss's law to figure out how the distance dependence goes, the Coulomb force would drop off as 1 over distance, not 1 over distance squared. And so this is indeed like Coulomb's law in the 2-dimensional universe. Okay, I see I am over time here, so I will stop and answer questions about this and then continue on Wednesday.